All right. Okay, so last week I talked about the characteristics of populations, the properties of populations. I talked about population size, density, and something else I forget. Today's topic is going to be how populations grow. So there's basically four, what do you call it? Four things that we look at. I can't think of the name specifically. The word, not criteria, but parameters for whatever. 4 factors. There we go. There's 4 factors that we look at to be able to calculate population growth rate. So you can see based on the graphic I have here, there's immigration, which are people being added to the population. You have emigration, which are people leaving. I was going to say people, organisms coming into the population. Emigration is organisms leaving the population. And then, of course, you have natality, which are births, and mortality, which is death. So these 4 things and the rate of these 4 things is going to determine the overall population growth rate. Scientists who study population dynamics are called demographers, and they define growth rate as the amount by which a population's size changes in a given amount of time. Whether a population grows, shrinks, or stays the same depends on these 4 processes. Again, immigration are organisms that come into this population from an outside population. Emigration is leaving, births and deaths. So you have birth, death, emigration, immigration. As I said, immigration is moving into a population. Emigration is out. To make things simple, demographers usually assume that emigration and immigration are 0. Doing this allows growth rate to be expressed as an equation, which is represented by birth rate minus the death rate is equal to the growth rate. I think a better way to say this point is basically to assume that the same number of organisms that come into a population is balanced by the number of individuals leaving the population. So immigration and emigration basically balance each other out, so they don't have to worry about that. So you take the number of births minus the number of deaths, and that's how much your population grows. For example, if we have 52 births and 14 deaths per 1,000 individuals, the per capita or per person birth rate is 0.052. That's 52 divided by 1,000. The per capita death rate would be 14 over 1,000 or 0.014. So the growth rate would be 0.052 minus 0.014, which equals 0.038. That is growth per capita. Again, per capita is per person. So this allows us to predict how many more individuals will be added in future periods of time. So we can calculate how much a population will increase next year. So we take the growth rate times the number of individuals currently in population. That's going to equal the number of new individuals that will be added in the following year. So if we have 50,000 people in the previous example as a total for the number of individuals at this current time, and we multiply it times the growth rate that we calculated, 0.038, that means that next year we will add 1,900 new individuals. So the new total population will be 51,900. If the growth rate is a positive number, remember this is the growth rate, that means that the population is growing. If it is a negative number, that means the population is shrinking. And I I don't know if it was your class or another class I was talking to about I think it was the, not just the biological impact of population growth, but also the economic impact. It turns out that demographers have been studying human population growth, especially in Western countries. And it's been the case in Japan for a long time that their population growth is negative. And so they're having a really big problem. Even if you look at China, for example, they had a one-child policy for many, many years. I can't even remember how long that was. That because their population was so big that the government came out and said you can only have one child. So that resulted in, of course, there's always accidents, right? Hold on, Owen wants to come in. Okay, so for pregnancies, there's always going to be pregnancies that are accidents. And so it turned out that for many years in China, that people would accidentally become pregnant and then they would basically like dump their baby on the side of the road or whatever, because it was illegal, like literally illegal for them to have a second child. The other problem is that culturally, boys are more desired, according to what I've read. Okay. So in previous years, boys were more desired than girls were. So because Chinese people were only allowed to have one child, and society in China says the boys are better than girls, then if they had a girl, that would be their only child they were allowed to have. There were a lot of stories about young baby girls being left out in the middle of like the side of the road to die because they just didn't want to have their one child be a girl. The problem now is that, or over the last couple of years, China is realizing that because of their one-child policy and because of their patriarch, a patriarch, if you don't know, patriarch, the prefix pate means male. So paternal or patriarch is a male-dominated society. And because of the patriarch, they don't have enough females now in the current Chinese population. So that's why I don't know when it was. I'll have to look it up. What year exactly China rescinded or took back their one-child policy? It was quite recently, I think, in the last few years. So now Chinese people are allowed to have, I don't know if they're allowed to have as many kids as they want, or they're just allowed two. I'm not really sure because I haven't read too much about it. But I do know that they took back their one-child policy because they realized, wait, we don't have enough females in population to actually keep the population not only just stable, but like we could end up being in a negative growth situation. So how does negative growth actually affect a society economically? Well, think about, and I don't know like how much you learn about civics or how like societies like work as far as economically. So you have let's say in the population of Thailand, I don't know if if Thailand's population growth, I can look it up real quick. Thailand population growth rate. Excuse me. Ooh, that's not good. 0.3%. I'll just put it up on the screen because this affects you guys. Come on. Oh no, I don't want to open Firefox. I want the menu bar to go away. Let me stop that and I will share. Hold on. Desktop is just easier because then you see everything. Firefox, go away. Oh, my computer's having real problems at the moment. Okay, that's why I'm trying to back all my stuff up. Let's move that way. Okay. Oh, here we go. So you can see Thailand's population growth rate is only 0.3%. That is lower than average. I think average would be about 1%. 2% is high. But look at this. Over the last 20 years, Thailand's population growth has decreased significantly. In 2000, it was average 1%. Yeah, perfect. And it's only decreased over the last 20 years. And there could be a lot of reasons for that. If you look back to, look, it used to be over almost 3%. That's huge. 1966, 3%. That's probably when I would say maybe your grandparents, grandparents, around that, their generations. And it's just declined. Look at that huge sharp decline in the 90s, went a little bit up from like mid 90s to 2000, and it's just completely dropped off. So the reason why this matters is because of economics. And the reason why economics matter is because, oh my God, why is this? Hold on, sorry. Close this, close tabs, geez. Just quit the program already. All right. The reason why that matters is because economically, we cannot work forever. So you cannot make a living forever. And so what happens is when you retire, generally, people have what's called a retirement fund, and a lot of, like, when you start working, your taxes pay for that. And so part of your taxes go to your retirement fund. And so you work for, let's say, 40 years, and then you retire. You might have your own private retirement as well, but the government, because you pay taxes to them, that's kind of insurance to say, okay, when I retire later in life, you're going to help support me, right? But if there's fewer young people working, then imagine the government has like a big bank account that's like for retired people to support them. If there's less people working, that means there's less taxes being paid, which means that bank account gets smaller and there's not enough money to support the number of older people. Because remember, if you, oh, got a frog in my throat. If I go back to that here. Can I just, yeah. If we go back to this and think about the fact you guys were born, what, 2004, 5, something like that. So the number of people when you guys retire, if this trend keeps going, there's going to be fewer and fewer young people working by the time that you guys get ready to retire. And so that's why it matters. And that's why it's important to make sure that people keep having babies. But for many reasons, people are just, sorry, if we're going to figure out what's happening here. Okay. For many reasons, people are not having kids, which is totally fine. I mean, you should not have children just because of the population growth. I mean, that's just a stupid reason, but just letting you know, that's how it affects us, not just in the context of biology, but also politically and economically as well. So we have a couple of models that we can use to describe population growth. One of them, what you see here, is called the exponential model, which I'm sure you recognize this curve as an exponential curve. You should have seen that in math. If the population increases rapidly after only a few generations, and the larger the population gets, the faster it grows, this is called exponential growth. I would say almost all species encounter limitations on exponential growth. You don't see, except for maybe humanity, because we have technology and medical advancements and things like that that prevent us from dying at an earlier age. It would be interesting to look at the life expectancy, say 50 years ago versus today. We are living longer and longer. But in nature, there are limitations that prevent populations from going out of control. So how does the exponential model match the population growth pattern of a real population? Because basically, if there are no limitations and you have an infinite amount of living space, an infinite amount of resources, an infinite amount of food, yada, yada, then any population has the potential to grow exponentially, but they don't. So then it's the job of scientists to look at, okay, because we know that we can see populations don't grow out of control. What are the factors that limit population growth? Populations can grow exponentially, but only under rare conditions for short periods of time. A really great example of an organism that goes through exponential growth is bacteria. You can look at bacterial growth videos on YouTube, and you can see that they explode, but they come to a certain point, which you can see in this graph. There comes a certain point where they just cannot grow anymore, whether it's a lack of space, a lack of food, whatever it is. So populations cannot grow forever. The main reason is limited resources. You also have the buildup of wastes. If you think about just the human population, we produce waste, not just like biologically, but like garbage, right? Where does our garbage go? So we have something called a limiting factor. These are factors that control population growth. As a population grows, you have an increased competition, you have fewer resources per individual, and this reduces both growth and reproduction. Now, the more accurate model to describe population growth is something called the logistic model. This builds on the exponential model, but it also takes into account limiting factors, which you can see down here. For the logistic model, we introduce something called the carrying capacity, which we label as K. This is the number of individuals that an environment can support over a long period of time. Now, the carrying capacity, of course, is going to be specific for the kind of environment and also the organism. So the carrying capacity for, let's say, a population of deer is going to be different than a population of, let's say, squirrels in the same area, because they use different resources. Sometimes they use the same resources. So it just depends on the population and location. For a small population, the birth rates are going to be high and death rates are going to be low. As the population approaches K, the growth rate is going to start to fall because you have the birth rate, which is going to start to decrease, but you're also going to have an increase in death rate. And it makes sense if you think about it, like the older a population is, you're going to have more older individuals that reach the end of their life and they will start dying. So this is called logistic growth. This is a more accurate model for population growth. The logistic model still contains assumptions, however. First, it assumes that carrying capacity is constant and that it doesn't change. In reality, of course, I would actually really love for you guys to do research on this, because it's something it's been mentioned in the news a little bit, but climate change affecting, what do they call that? Oh shoot, I just had the term in my head and it just went right out of my head. But basically it's climate change is creating refugees, because there are parts of the planet which are now becoming uninhabitable because of climate change. And therefore, the carrying capacity for those kinds of environments is going to be reduced drastically because the environment just doesn't support life anymore. And that is creating, what do they call that? Ecological refugees or climate change, something. I'm going to have to look that up, and maybe I can come up with some kind of research project for it, because it is a more and more pressing issue. And of course, that has, what do you call that? It has repercussions both economically and politically, because where do those people go, right? I know that in America, there's a lot of concern over refugees and like a lot of, let's just be honest, racist white people that are like, well, this country is ours, we don't have any more room. But you have this kind of sentiment, like what happens in Thailand if you've got like surrounding countries that have people that are fleeing their homes because of flooding, and that they're just completely flooded out of their home? Does Thailand say, okay, you can come and live here? If you do, like, do we provide you with a place to live or jobs, visas, all of that kind of stuff? How do you welcome new people into your country and make them a part of society? So climate change has a huge effect on carrying capacity and what happens to us in the future. So in reality, carrying capacity does change because the environment is always changing. It's one of the first things that I mentioned when we started talking about ecology. The carrying capacity, just speaking on a strictly like natural kind of thing without talking about humanity, because we are kind of, I guess, sort of above nature in a way. If you're talking about a predatory species, if there is a large population of prey, then the carrying capacity increases for the predators. So for example, let's just go with like fox. And what do foxes eat? Let's say, I guess they eat squirrels or chipmunks or rats, whatever. If the population of the animals that foxes eat is high one particular year, then that supports a higher or a bigger population of foxes. If maybe like, if you think about, let's just use mice. So you got fox, eat mice, which eat, what do mice eat? Grass. Now, let's say there is, this year, there's a huge drought, which is when it doesn't rain. And let's say the drought kills half the grass. So you have half the grass, which means you've got half the mice, which means you're going to have approximately half the foxes. Or normally it's magnified. There's something called biomagnification, which is the effect that it has on the next trophic level up is exponentially worse. So if half the grass is gone, maybe you have, oh, of course, my Bluetooth. Thanks, buddy. Or at least that's still up. Where am I? Oh, no, now it's gone. Okay, it's fox, mice, grass. So if, let's say in 2022, we have big climate problems. So let's say you're down to half the amount of grass, which means you maybe get a quarter of the amount of mice, which means maybe you have an eighth the number of foxes. So that is how carrying capacity can change. Now, there's two kinds of limiting factors that can control population size. One are density independent factors. These reduce the population by the same proportion regardless of population size. So a lot of these you can consider like climate change, natural disasters, anything that doesn't depend on how big the population is. So the weather, floods, fires, a lot of the things that we're seeing with climate change, it doesn't matter if the population is 1 or 100 individuals, it will affect the population the same way. It's not going to change. Two, obviously, is going to be density dependent factors. These are totally going to be determined by the size of the population. Really obvious density dependent factor is resources, the amount of food, living space, nesting sites, that kind of thing. If you only have one individual, then you don't have to worry about limited amount of food. If you have 10,000 individuals for the same area, then the amount of food becomes a density dependent factor. Of course, all populations fluctuate in size. Some fluctuations are clearly linked to environmental changes. You can see, for example, if one year is hotter than the next year, or if there's more or less rain, you can look at those environmental changes and then see their effect on population size. For example, drought, again, a lack of rain, reduces the population of deer in a forest. But some fluctuations are not connected to the environment. So explaining those fluctuations is much more difficult. You have to try to identify, if there are limiting factors, what those factors are. A study that was a well-studied example of population fluctuation is with the lynx, which is that cat you see there, and the snowshoe hare. So the lynx preys on the snowshoe hare, and you can even see, just without even explaining the whole thing about the guy and whatever he went up to. I think it was like probably northern Canada, or maybe, yeah, up really, really far north. The hare is in green and the lynx is in red. You can see here, if you have a spike in hare population, shortly after that, you will see a spike in lynx population. And when you see a decrease in hare population, you're going to see a decrease in lynx population. Same thing here the next year, or 5 years later, whatever. So you see there's a regular ebb and flow. I think ebbing is down and flow is up. Regular ebb and flow of the hare population, and it always coincides with the lynx population. So here in 1865, huge spike, the biggest spike you see of all, whatever, almost 100 years we have here. And you have almost the largest spike, except for this one, in the lynx shortly after that. So it's easy to make a correlation between the population of hares and the population of lynx after that. So the scientist who did this was Charles Elton, and he didn't actually go out and count the rabbits or the hares. He kept track of the pelts that were bought from trappers for the snowshoe hares. So of course, like we use rabbit fur, rabbit pelts for coats and shoes and things like that. So he assumed that the number of pelts that were bought from the trappers showed the size of the population. It makes sense, because if you have a lot of rabbits that are caught in traps, that means that the population is bigger than if you have fewer. So the records showed the hare population cycle lasted about 10 years. So every one of these peaks is about 10 years between the cycle. Then he also looked at the lynx pelts, and the cycle peaked about 1 to 2 years after the hare population, which is why you have that slight delay in the red lines after the green lines. So Elton hypothesized that each species was the cause of the other's cycle. So you can think about the fact, if there's more hares, there's more food for the lynx. But when the population of hares declines, there's less food, which means the lynx are going to also decline after that. And it makes sense, because if the hares increase, there's more food, there's more lynxes. But if there's more lynxes, then there's more predators preying on the rabbits, which means there's less rabbits or hares. Okay, less hares, less food, less lynx. So they kind of cause each other's rise and fall. When there's less lynx, there's less predators, which means the hares are going to start to increase again. And that 1 to 2 year delay is probably the cause of the 10-year cycle between both of them. Okay, next is when you have a population that is endangered. Now, I just downloaded a book called The Sixth Extinction, I think, because we are in the middle of in the history of Earth, there have been 5 mass extinctions. A mass extinction is marked by a record number of species going extinct in a very short period of time. And we are in the middle of the 6th mass extinction. And it is basically, I think the consensus among scientists is that it is driven by the growth of human population. We're just taking up too much space. We are taking down too many habitats, and we're just destroying species everywhere. This is a picture of a Siberian tiger. There are fewer than 200 left in the wild. Now, there are several different categories of endangered. There's endangerment in the wild, which means there's still native species that live in nature, but they're endangered. You also have extinct in the wild, which means they're not completely extinct, but they don't exist naturally anymore. They only exist like in maybe wildlife refuges or zoos. And the 2 main reasons, at least for the Siberian tiger, is overhunting. because of course it's a beautiful animal, and you have people that, and I don't understand the mentality, but people do have the mentality that they like to hunt animals and then display their, either like they'll skin the tiger and make it a rug, or they'll mount the head on the wall, something like that. But we're also the majority of the driving force behind a lot of the endangerment and extinction is coming from habitat destruction. The problem with small populations is that any change in the gene pool is going to have a huge impact. And of course, the smaller your population, the more susceptible you are to having an entire population killed by like one flood. There comes a point where there's just too few individuals to continue the species. Like that's why they take panda bears, and you might read a story every once in a while about a panda bear from China being shipped to maybe like San Francisco to the zoo there to try to make them reproduce, because there just aren't enough pandas going around. So they basically have to ship them around the world to try to have them continue the species. When you have too few members of a species left in the wild, you have a problem with something called inbreeding. And inbreeding is mating with relatives. Now, nature doesn't like this because nature likes to expand the gene pool, not shrink it. If there's not enough individuals left to reproduce, you end up with inbreeding. The offspring of related parents are fewer, which means if you have two related individuals, they won't produce as many offspring at one time. They're also going to be more vulnerable to disease, and they're going to have a shorter lifespan. These are all organisms that are on the endangered species list. So you've got the orangutan here. I recognize this is a puma or a mountain lion. That's the American bald eagle. This is a manatee, which lives in Florida. A lot of the problem with the manatee is that they live in estuaries, which are basically the areas where the river dumps out into the ocean. And that's usually in a wetland area. And a lot of places in Florida, they drain all of the water from the wetland to build condos and things like that. That's the jaguar, some kind of sea turtle. Here's the lynx. Lynx is endangered. Panda bear, of course, panda bear. Bleh. Polar bear. Okay, Bluetooth just quit again. Anyway, so these are examples of endangered species. Oh, and the red panda is down there. Now, last thing I want to talk about is, ooh, how did that go backwards? Weird. The Endangered Species Project. Okay. Now, I want you to find a species that is on the endangered species list. You can ignore the due date because this is from last year. And I want you to create a booklet or a pamphlet. Now, I have examples of this, and I am going to school today because I have to pick up my ATK testing kits. So I will take some of the previous projects home, and I can show you pictures of that. We don't have class on Friday. Maybe I'll take some pictures and I'll show you some examples, but it can be any species that is endangered. I just want basic information about the species, big point, the reason for the endangerment, okay? I want you to talk about the population trend over the last 50 years. And if there are any steps being taken to improve or protect the species. I will say it is due next Friday. I will also take a screenshot of this so I can put that in the line chat to make sure everybody knows. Okay. And yeah, next Friday, which is, I don't know what date that is. I think a week is long enough, but I really just want to kind of book pamphlet style. And like I said, I'll take some examples home and show you what I mean. Okay. That